today's video, we're going to be looking at series wiring of igniters because this is really a hot topic in fireworks about do you wire in series, do you wire in parallel? And generally people that deal with absolutes in this area don't fully appreciate the positives and the negatives of each method of wiring. And equally, some training, particularly in professionals that I have witnessed, doesn't really explain the full consequences of how you calculate this and how you fully appreciate what's going to happen when you press the fire button. So let's just have a quick look at some of the common issues that you often find relating to this. So the first one is you've fired a series of talons. So you've got a series circuit of talons. The first talon fires, nothing else fires. This is because unfortunately talons have to be wired in parallel. That is an absolute. You have to wire talons in parallel because they just ignite at different times, and the timings can be quite extreme. So it's not like an igniter where actually they tend to all fire within a very fraction of a second of each other. With talons, we could be talking 100 milliseconds, 500 milliseconds possibly between firing. It can be really delayed. So we have to make sure we have a full circuit that stays complete for the whole firing time. The next one that people often say happens is that they've extended their E matches or their talons, and then the circuit doesn't fire, and they're not quite sure why. And that in that case could be because the circuit resistance now is too high because of the additional cable you've added. Another one that often gets asked is that somebody's connected, for example, 5 E matches in parallel and none are fired at all. And this is to do with parallel current drop, but that's not in this video. We'll discuss that in the next video. And then the last one is some people say, well, continuity showed good, but the circuit never fired. And this again is to do with resistance. So just because you have continuity and it shows it's good on some firing systems, that is not the same as doing a resistance check. So you'll find quite often in the high explosive industry, in blasting, for example, they'll use ohm meters or galvanometers to actually measure the resistance of a circuit rather than just to see if it's complete, because that's what a continuity does. Continuity just shows you if the circuit is complete, not if it actually has a low enough resistance that the power supply attached to it will be able to fire it. So let's now move into series circuits, which is what we're going to be doing today. So here we have a basic series circuit of this is E matches or igniters. So we're not talking about talons again. Talons have to be wired in parallel. So this video does not talk about talons at all. So this is some igniters. We have 5 meter igniters, 3 of them wired in series. We have 2 PP3 batteries, so 2 9-volt batteries. And we're also going to say that we want a minimum of 0.5 amp to fire these igniters, because usually 500 milliamps is the surefire current listed on most igniters. Okay, so to work this out, we will use, first of all, we'll find out what the resistances are. So we know that just the wires alone, that 5 meters of the wire gauge for this igniter is going to be about 0.26 ohms. And we have 2 5-meter wires attached to every igniter. So even though you have 5 meters of igniters, you've actually got 10 meters of cable. So that actually means that overall the whole circuit, just in cable resistance, is about 1.58 ohms. On top of that, we also have the resistance of the igniter heads, which is that little fuse wire that sits on the little circuit board below the ignition material. And that generally is around 1.2 ohms, we're going to say, for this. Lots of igniters you'll find when you look at the data sheet will give you the whole resistance of the igniter plus the cable rather than just the cable and the igniter. It's usually just the whole one, but in this case we're going to separate it. So that means we've got about 3.6 ohms in total. So if we now add these together, we know that in series, that basically the sum of all resistances, that gives us 5.18 ohms. Now we can use Ohm's law at this point. So we can say, well, 18 volts divided by 5.18 ohms gives us 3.47 amp. So we're going to say to ourselves, that's brilliant. That's enough to fire our igniters. Why is that enough? because we know that the total current must be larger than the igniter minimum surefire current to guarantee firing. And we know that our minimum surefire current is half an amp, and we've got 3.47 amps according to Ohm's law. Excellent. But now we've got a big issue here because we've missed some resistances out. And the resistance we've missed out is actually at the power supply. So, in actual fact, we have to include the battery resistance in this calculation as well. And I've said we've got two PP3 alkaline batteries, which effectively have about 1.7 ohm resistance each. And now we've got another issue here, because how do you measure the resistance of the battery? And what is the resistance of the battery? And this depends on the battery chemistry, and it depends on the load that you put in it, and it depends on the temperature. So there is no real fixed resistance when it comes to battery resistance. Different types of batteries will have different internal resistances. Generally, the PP3 alkaline is one of the highest internal resistances, but also you'll find the temperature will also make a big difference. If you operate a battery in a very, very cold environment, then the resistance will be much higher than if you operate it in a very, very hot environment. And this can cause some issues for people when they're firing in very, very cold weathers and very, very cold places like Canada, for example, where you might have very low temperatures overnight, which you could be firing in, because suddenly your current in your circuit will drop because you've got larger resistances in your circuits. But let's just assume we have this fixed resistance, that we know what it is. We're going to fire in a temperature which won't change this, and see what that does to our firing current. And you can see I've just quickly done the calculations right there. We've added an extra 3.4 ohms to our circuit. So now we have about 8.58 ohms, which means if we do our Ohm's law again, we have about 2.09 amp. So we've got a drop of about 1.38 amps from adding the internal resistances. If we go back a minute, so you can see we've gone from 5.18 to 8.58. Now, we have another problem here, because Ohm's law, unfortunately, does not give us all the information we need to know about this circuit, because we've talked about now the battery resistance, and I've said about the battery resistance changes with temperature. It can also change with age as well as charge. So for example, like a lithium based battery, generally as they get older, the internal resistance will get higher. You'll also find some battery chemistry that as the battery gets discharged, the resistance gets higher. So during this we've got this battery resistance issue now we've got to take into account. But now we've got the issue that Ohm's law is lying to us, because if we had two PP3 batteries, then the battery chemistry wouldn't supply 2 amps. You'd be lucky to get 1 amp. So Ohm's law is now wrong. Ohm's law has lied to us. Or has it lied to us, I suppose, is the question. And the answer is the problem with Ohm's law, and with lots of formulas that are spoken like this and told and educated to people like this, is that it doesn't really look at the parasitic effects of circuits. Everything in this circuit is looked at as being the perfect model. So we have a perfect power supply that gives us a voltage, and we can have endless amounts of current we can calculate from it. And this is just not true. This is not the realities of the world around us. So we have to also look at the battery we're using and the chemistry of the battery and how that will affect us. Now, the numbers you're seeing on this slide are very estimated, I would say. These aren't the exact numbers because it's very difficult to find exact numbers in this world when it comes to these sorts of chemistries and that. And to be honest, the data sheets don't tell you, and manufacturers aren't precise. And people often get confused between things like milliamp hours and peak current because they're not the same. They're two different measurements. So what I've tried to do is I've tried to look at each of these types of battery, and I've tried to give you a rough ballpark figure of what you could expect if you made an absolute dead short on the battery, what the chemistry could do. You wouldn't necessarily want to do this because you damage the battery. But if you have a look, so for our 9-volt batteries, if we had they're roughly 550 milliamp hours, or you can go as low as 300 milliamp hours. It depends on the battery you buy and who's it from, etc., and the chemistry in it. But generally, it's accepted that you may be able to get about a 1 amp peak from a 9-volt battery. And bear in mind, just because we've got 2-volt 9-volt batteries in series, that doesn't increase the current capacity. Yep, it increases the voltage but not the current capacity. If you want to increase the current capacity, you want to put the batteries in parallel, but then you don't get the increase of voltage. So you'd get 9 volts, but you'd get an increased current supply. But in this case, we've got 2 batteries in series, which gives us our increased voltage, but does not give us an increased current capacity. So 2 9-volt batteries would give us about a 1 amp peak if we're lucky, if we're on a good day. The LiPo battery, which you can see here, which is quite common in this chart, sorry, is also from the Cobra website, by the way. This is not my chart. This is what Cobra suggests. Their 14.8 volt LiPo gives you about 2 amp peak, I would say. 12 volt external battery. Now, what 12 volt battery are you looking at? Most lead acid batteries, which will be 12 volts, usually, for example, like 7 amp hour or 10 amp hour, it's usually very high current sources. And if you were to short that, you would get a stupid amount of current. And some data sheets will say, from anywhere from 60 amps to 150 amps. And that is, sorry, when I say amps, I mean amp, sorry, because I'm not saying amps per second, I'm saying amp. 150 amp, which would melt everything. It would just completely destroy the battery and the leads and everything, because that sort of current flowing would be horrendous. And equally, on the 18.5 volts, this is still using lead acids. And then again, 24 volts, you had 2 lead acids in series. Again, if you look, the peak current and the milliamp hours are the same because they're in series, not in parallel. So we can see that our original Ohm's law that told us we're getting 2.09 amp can't possibly be true, because our 9-volt batteries only give us a 1 amp peak. So how do we actually calculate this that could give us not a misleading result? And the answer really is to understand what is the peak that your battery can deliver, and then calculate that in relation to the igniter. So we want to try and sort of just change the way we're calculating a little bit. We just move Ohm's law a little bit. So again, we've got the same circuit and we've got the same resistances. And what we're going to say now is, rather than use the resistance as our primary form of calculation, so originally we did V over R, now we're going to do V over I, because then we can use 0.5 amps, which is our minimum firing current, as our current in the formula, because we know our battery can supply 0.5 amps. Yeah, so therefore we can use that in our formula. So we're going to do 18 volts divided by 0.5 amps. So we know our maximum resistance is 26 ohms. If we calculate our resistance as bigger than 26 ohms, we're not going to get that half an amp. So we shouldn't be using that circuit. We could be more generous. We could say, well, actually, we want at least 1 amp just to make sure it absolutely does fire. In which case, 18 ohms now becomes the largest resistance we can use in our circuit. And you'll notice that obviously when if you're going to use 1 amp as a basis, you'll find that it basically divides off. So if you had your 14 volt LiPo, you would have about a 14 ohm maximum load, etc. So this comes to a slight sort of junction now, because we've got this idea, what are the pros and cons? We've done some calculations, we've realized there's some holes we can fall down. So generally, in series, all igniters will receive the same current. The same current flows through every igniter in the circuit. That's one of the big advantages of this. So if you know you've got 1 amp flowing, 1 amp is going through all the igniters. Also, continuity shows if all the igniters are complete. So you know all your igniters are supposedly good. They're all making a circuit. Again, that does not tell you that circuit's going to fire. You could get continuity on a very high resistance circuit and you believe that's good, and then it won't fire. Some firing systems will be mindful of that, so they won't show continuity on high resistance circuits. Other cons are if one igniter fire opens, obviously, others may fail to fire. So if one fires quicker than the others. Again, this is not appropriate for use with talons. It is not suitable for high resistance circuits because of the fact that you have resistances that are all adding up in a series, and therefore you're dropping the overall circuit current. If you want to maintain the same current, you would need a higher voltage, and battery series resistance also should be added in to your calculations. So there we have it. We've discussed how to wire igniters into series and the pros and cons of series, and the dangers of not understanding the formulas of the battery technology you have. So in the next video, we will look at how parallel circuits work, and there are some big cravats in that, believe me, because some people can really fall into some ridiculous numbers using variations of Ohm's law with currents which are just completely unavailable to you in this circuit. But because of the low resistances, it fools you into believing that you can create these huge currents that will allow almost anything to fire. And again, we've got some big problems with that. That won't happen. So there you go. That's the series circuit.